Today we are going to discuss about the application of group theory to electronic spectra of formaldehyde. What we see on the screen now is a Cartesian coordinate system. The x, y and z axis, and now sigma xz, which is the xz plane, is shown. The sigma yz, the yz plane, is shown, and the sigma xy, the xy plane, is shown. This is the structure of formaldehyde. The carbon atom is sp2 hybridized, and so the structure is trigonal planar. The C2 axis is along the carbonyl group, passing through the carbonyl group. The sigma xz plane is a molecular plane containing all the atoms of formaldehyde. The molecular plane is sigma xz. The sigma yz is a plane passing through the carbonyl bond perpendicular to the molecular plane, bisecting the two carbon hydrogen bonds. One of the carbon hydrogen bonds is in front of the plane, whereas the other carbon hydrogen bond is behind the plane. So sigma yz is perpendicular to sigma xz, that is the molecular plane. The symmetry operations in formaldehyde we have seen are E, the action of doing nothing, C2, the principal axis passing through the carbonyl bond, sigma xz is a molecular plane, and sigma yz is a plane perpendicular to the molecular plane, cutting through the carbonyl bond, bisecting the two CH bonds. And these four symmetry operations constitute the point group of C2V. So formaldehyde belongs to the point group C2V. Now we are interested only in the carbonyl bond. It contains one sigma bond which is formed by head-on overlap of the sp2 orbitals, the pi bond which is formed by the lateral overlap of 2p orbitals, and the non-bonding electrons over oxygen. Now we are going to apply the four symmetry operations of C2V point group, namely E, C2, sigma xz and sigma yz to the sigma molecular orbital and sigma star molecular orbital, the pi molecular orbital and pi star molecular orbital, and the non-bonding orbital, and see what happens to the signs on these orbitals during these four operations of E, C2, sigma xz and sigma yz. Now what we see is the molecular orbital formed by the head-on overlap. This is a bonding molecular orbital. The signs are identical, both are positive signs, and we apply the four symmetry operations, namely E, C2, sigma xz and sigma yz to this sigma molecular orbital and examine the behavior. When we do the operation E, the operation of doing nothing, nothing happens, and when there is no change in the signs, we represent it as 1. And now we apply the C2 operation over the sigma molecular orbital. Both the lobes of the sp2 orbital are present in the C2 axis itself, that is, we make a rotation of 180 degrees and the two plus signs are not changed, and so we have 1. When we apply the sigma xz operation to the sigma molecular orbital, both the lobes of sp2 orbital are present in the molecular plane itself. There is no change in the sign, and so we get 1. When we apply sigma oz, this is the plane that cuts through the two lobes of sigma molecular orbital perpendicular to the molecular plane. The signs are unchanged, and so we get 1. Now if you look at the character table of C2b, here we get 4 1s, and we have 4 1s, the same sequence. The symmetry is A1, and so the symmetry of sigma molecular orbital in formaldehyde is A1. Next we go to the sigma star molecular orbital. What we see is, in the case of sigma molecular orbital, both the signs are plus, whereas in the case of sigma star molecular orbital, one lobe carries a plus sign, the other lobe carries a minus sign. Now we apply all the 4 symmetry operations to the sigma star molecular orbital. First we apply the identity operation of doing nothing. The signs are retained and we get 1. And when we apply the C2 operations, that is rotation through 180 degrees, we find that the sigma star molecular orbital lies along the C2 axis itself, and so the signs will remain unchanged upon 180 degree rotation, and so we get 1. Next, when we apply sigma xz operation, there is a molecular plane. This molecular plane contains the plus and minus lobes of sigma star molecular orbital, and so upon reflection the signs are not changed and you get 1. Then we apply sigma oz operation to the sigma star molecular orbital. We get the signs remaining unchanged because this plane is perpendicular to the molecular plane, passing through both the lobes of sigma star orbital. Since both the lobes of sigma star orbital are present in the plane itself, the signs are unchanged and you get 1. Look at the character table. There is a sequence of 4 1s. This corresponds to A1, and so the symmetry of sigma star molecular orbital is A1. Now what you see is 2 p orbitals, 1 over carbon and 1 over oxygen, which is perpendicular to the molecular plane, and when they undergo lateral overlap above and below the molecular plane, you get pi molecular orbital, and we apply the 4 operations of C2v point group to this pi molecular orbital. E is the action of doing nothing. Everything signs remain unchanged, and so the number is 1. Next we apply C2, that is rotation through 180 degrees, and when you rotate it through 180 degrees, the 2 positive lobes will come to the bottom, the 2 negative lobes will go to the top, so signs are changed, and so instead of +1, now you will get -1, antisymmetric. When you apply the sigma xz operation to this pi molecular orbital, the sigma xz plane intersects these pi molecular orbitals. The positive lobes are above the plane. Upon reflection, negative lobes will go to the top, the positive lobes will come to the bottom, and so the signs are changed, and so we get -1. When you apply the reflection sigma oz, that is the plane which is cutting through both the p orbitals, which is cutting through the positive lobes as well as negative lobes. The sigma oz is also perpendicular to the molecular plane. The lobes are present in the plane itself, and so signs will not change. The positive will remain in the top, the negative will remain in the bottom, and so we get the number as 1. And if you look at the character table, here you find the sequence 1 -1 -1 1. Here also we get the sequence 1, -1, -1 and 1. This corresponds to B2 operation. So symmetry of pi molecular orbital is B2. Here you find that both the lobes on the top as positive, both the lobes at the bottom as negative. When you come to pi star, this is plus, this is minus on the top. On the bottom, minus and plus. And this corresponds to pi star. Now we will apply the four operations. Operation of doing nothing, signs are unchanged, and then we get 1. Next, when you apply C2, that is rotation through 180 degrees, the bottom lobes will come to the top lobes will come to the bottom, and so the signs will change, and so the number is -1. Next we get sigma xz. When you apply sigma xz operation, that is the plane corresponding to the molecular plane, 2 lobes are above the plane, 2 lobes are below the plane. Upon reflection, the top lobes will come to the bottom, the bottom lobes will come to the top, and so the signs will change, and so the number is -1. When you apply sigma yz, that is the plane which cuts through all the 4 lobes of pi star molecular orbital, which is perpendicular to the molecular plane. Since all the lobes are present in the plane itself, the signs will not change, and so we get +1. And when you look at the character table, the same sequence 1, -1, -1, 1, 1, -1, -1, 1. And so the symmetry of pi star molecular orbital is B2. The non-bonding orbital is present over oxygen in the molecular plane, unlike the pi orbitals which are present perpendicular to the molecular plane. We will apply the symmetry operations E, C2, sigma xz and sigma yz to the non-bonding orbital present in the molecular plane over oxygen atom. When we do the operation E, that is the action of doing nothing, the signs are unchanged, and so the operation is symmetric, and we get the value as 1. When we do the rotation about the C2 axis, the signs are changed. The negative lobe becomes positive lobe, and positive lobe becomes a negative lobe, and so it is antisymmetric, and so the number is -1. When we do the reflection about sigma xz, which is the molecular plane, since both the lobes of the non-bonding orbital are present in the molecular plane, the signs are unchanged, and so the operation is symmetric, and the number is 1. Next we come to sigma yz plane. It is perpendicular to the molecular plane. It cuts through the carbonyl bond. The negative lobe is in front of the plane, and the positive lobe is behind the plane. And when you do sigma yz, that is the reflection about sigma yz, the negative lobe goes to the back and positive lobe comes to the front, and the signs are changed, and the operation is antisymmetric, and the number is -1. We get 1, -1, 1 and -1. If you look at the character table, we see the same sequence 1, -1, 1, -1 against B1, and so the symmetry of non-bonding orbital is B1. Now, if we summarize whatever we have discussed so far, for each molecular orbital, we have applied the 4 symmetry operations of point group C2V, namely E, C2, sigma xz and sigma yz, and found out the behavior of these 5 molecular orbitals: sigma, sigma star, pi, pi star, and non-bonding molecular orbital. We will summarize them now. For sigma, we got the symmetry as A1. For sigma star, we got the symmetry again as A1. For pi, we got the symmetry as B2. Pi star, the symmetry is again B2. And for the non-bonding orbital, the symmetry is B1. Now, we look at the carbonyl group. It contains sigma bond, pi bond, and non-bonding electrons. We will take one pair of non-bonding electrons, and so the ground state configuration for the orbitals is bonding sigma molecular orbital containing 2 electrons, the bonding pi molecular orbital containing 2 electrons, and the non-bonding electron containing 2 electrons. So, considering only the 2 electrons present in the non-bonding orbital. And now, if we see here, the symmetry corresponding to sigma molecular orbital is A1 that we have found out earlier. And so, we are substituting the symmetry corresponding to sigma molecular orbital A1 here, and the symmetry corresponding to the pi molecular orbital is B2. We are substituting it here. The symmetry corresponding to non-bonding orbital is B1, which is substituted here. Now, if you look at the character table, A1 is all ones, all plus ones, and if you square it, it's once again all plus 1. And so A1 square is A1. B2 is 1 minus 1 minus 1, 1. And here you have B2 square. And if you square it, square of minus 1s is plus 1. And so you get, when you square it, 1, 1, 1, 1, and that corresponds to A1. So B2 square is A1. If you look at B1 once again, 1 minus 1, 1 minus 1. And if you square B1, square of minus 1 is once again plus 1. You will get A1 once again. And if you take the product, it's A1 once again. So the symmetry corresponding to ground state configuration is A1. Next we come to the N2 pi star excited state. So one electron available in the non-bonding molecular orbital. This is moved to the antibonding pi star molecular orbital. That is what is known as N2 pi star. The other electrons remaining as usual. 2 electrons in sigma and 2 electrons in pi. The symmetry element corresponding to sigma is A1. The symmetry element corresponding to pi is B2. The symmetry element corresponding to non-bonding orbital is B1. So you find the B1 here. The symmetry element corresponding to pi star is B2. And so instead of pi star, you put B2. A1 square is A1. All plus 1. Square of plus 1 is plus 1. B2, 1 minus 1 minus 1, 1. If you square them, all become plus 1. That corresponds to A1. Now, the other two things, B1 and B2, they are not squares. You cannot simply square them. Instead of that, you have to take the product of B1 and B2. That is, B1 and B2, product of the characters of B1 and B2. 1 into 1 is 1. Minus 1 into minus 1 is plus 1. Minus 1 into 1 is minus 1. And 1 into minus 1 is minus 1. So, the product of B1 and B2 is nothing but A2. The symmetry of N2 pi star excited configuration is, now we come to pi 2 pi star. That is, the 2 electrons present in the sigma molecular orbital, the ground state is present as usual. And the 2 electrons present in the non-bonding molecular orbital is present as usual. But 1 electron which is present in the pi molecular orbital has moved to the antibonding pi star molecular orbital. That is what is known as pi 2 pi star. See, the symmetry corresponding to sigma is A1. The symmetry corresponding to pi is B2. The symmetry corresponding to non-bonding orbital is B1. The symmetry corresponding to pi star is B2, and A1 square is A1. B2 square is A1 because the square of the negatives becomes positive, all positives, A1. B1 square is A1, the square of negative characters become positive, all positive, A1. And net result, we get all the symmetry elements A1, the product is A1. Symmetry of pi to pi excited state configuration is A1. Now we will come to sigma to pi star excited state. That is, 1 electron present in the sigma molecular orbital has moved to the pi star antibonding molecular orbital. The other two electrons present in the pi remaining as usual. The other two electrons present in the non-bonding molecular orbital remaining as usual. The symmetry of sigma is A1. Symmetry of pi is B2. Symmetry of non-bonding molecular orbital is B1. The symmetry of pi star anti-bonding molecular orbital is B2. Look at the character table. This is A1. B2 square, if you square it, become all positive, A1. B1 square, all the characters of B1 become positive on squaring, and so we get A1. B2 is not B2 square, only there is only one electron, B2 power 1, and so it remains as B2. So symmetry of sigma to pi star greater state configuration is B2. Now we come to sigma star greater state configuration. One electron in the sigma molecular orbital moves to anti-bonding sigma orbital. So you find only one electron in the bonding sigma molecular orbital, whereas you find one electron in anti-bonding sigma molecular orbital. The other electrons remain intact as in ground state in the pi and non-bonding molecular orbitals. The symmetry of sigma is A1. Symmetry of pi is B2. Symmetry of non-bonding molecular orbital is B1. Symmetry of anti-bonding sigma molecular orbital is A1. A1 all positive. B2 square, if you square this B2, becomes all positive A1. B1 square, if you square all these characters, it becomes all positive and becomes A1 and A1. And so overall A1, symmetry of sigma to sigma excited state configuration is A1. Now, having found the symmetry corresponding to all these ground state as well as excited state configurations, this is ground state into pi to pi star, sigma to sigma star, excited state configuration. Now, which of these transitions are allowed, which of these transitions are not allowed, that is forbidden. By looking at the dipole moment vectors, they correspond to the x, y and z in the character table, which are present against the irreducible representations in the character table. And if they are x, y and z is present, then the transition is allowed. Remember, we are not talking about x, y, y, z or x, z or a square or y square or z square. They are the quadratic terms. We are looking at the Cartesian terms carrying power 1, x, y and z, and if they are present against the corresponding irreducible representation, then the transition is allowed. Here in this table we find the symmetries corresponding to the various states, ground states and excited states, which we have discussed so far. Now, if we take the n to pi star excited state, we have to take a direct product of the symmetries of ground state and excited state. The symmetry of ground state is A1. For n to pi star excited state, the symmetry is A2. And if you take the direct product, we will get it as A2. Now we look at the character table. Corresponding to A2 irreducible representation, look at the terms at the end. Do you find x or y or z Cartesian terms? Don't look at xy. Xy is a quadratic term because x power 1 and y power 1. If you take the sum of the powers, you will get it as 2. 1 plus 1 will become 2. It is a quadratic term. You have to look at x power 1, y power 1 and z power 1. You don't find any of this against A2. And since they are not present, this transition, that is n to pi star transition, is not allowed. Now look at the pi to pi star exciting state and take the direct product of the ground state and excited state. Ground state is A1. The excited state corresponding to pi star is again A1. And if you take the direct product, it is A1. Look at the character table. Corresponding to A1, you find the terms as Z, a square, y square, and z square. Since Z is present, the transition is allowed. Now look at sigma to pi star excited state. Take the direct product of the ground state and excited state. The symmetry for the ground state is A1. Symmetry for the sigma to pi star at the greater state is B2. And if you take the direct product, you will get it as B2. And look at the character table against B2. You will find Y as well as YZ. Since Y has a power 1, it is a dipole moment vector corresponding to electronic spectra. So, the sigma to pi star transition is allowed. Let's come to sigma to sigma star at greater state. Take the direct product of ground state and greater state. Ground state is A1. Greater state for sigma to sigma star is once again A1. We take the direct product, it comes as A1. In the character table against A1 you find the Z, and so the transition is long. Now we will summarize these results which I have found out just now. We find that n to pi star is not allowed, pi to pi star is allowed, sigma to pi star is allowed, but the other is forbidden, symmetry forbidden. And sigma to sigma star is allowed. The energy gap in the case of sigma to sigma star, this is sigma and this is sigma star, is very high, and so this will not happen. So out of this, the most predominant transition will be pi to pi star. N to pi star is not allowed. Sigma to pi star is allowed, but symmetry forbidden. Sigma to sigma star is allowed, but a high energy gap. But the significant transition will be pi to pi star. Thank you.